Today, we're going to talk about something you've probably used 1,000 times without a second thought, the humble thermometer. It seems so simple, right? But if we look a little closer, its design actually reveals some seriously deep physics. So let's dive in.
Let me start by asking you a question. You stick a thermometer under your tongue, or in a turkey, or you just look at the one outside your window. It gives you a number. But what is that number really telling you? I mean, yeah, it's how hot or cold it is, but the full story? Well, that goes much, much deeper.
So, to figure that out, we have to start with the fundamental problem. How do you even measure something you can't see? You can feel hot and cold, for sure, but you can't grab it, you can't weigh it. We need a clever way to make this invisible sensation visible, and something we can actually put a number on. Now, how we solve this is what's really interesting. Let's do a little thought experiment together. Imagine I hand you a glass tube with that silvery liquid, mercury, inside. But it's a complete blank slate. There are no numbers, no lines, nothing. How in the world would you turn that thing into a useful tool to measure temperature?
Well, it turns out there's a basic recipe for this, a universal set of instructions that's behind not just that unmarked mercury tube, but pretty much every single thermometer ever invented.
And here it is. It's a surprisingly simple, three-step recipe. First, you find what's called a thermometric property. That's just a fancy term for a physical trait that changes in a nice, predictable way with temperature. Second, you set some fixed reference points, things that happen at the same temperature every time, like water freezing or boiling. And finally, you just create a scale by dividing the space between those 2 points into equal parts, like degrees Celsius or Fahrenheit. That's it. That's the core blueprint for every thermometer.
And here's the really cool part. All those different kinds of thermometers you see out there, they're all just different tools using this exact same recipe. The only thing they do is swap out that first ingredient, the thermometric property. Let's take a quick tour and see how this one recipe builds a whole family of different devices.
Okay, so we'll start with the one we all know and recognize, the one from our little thought experiment, the classic liquid-in-glass thermometer. Its secret is just good old thermal expansion. Super simple. As the mercury or alcohol inside gets warmer, it expands, right? It takes up more space, and that pushes it up the tiny glass tube. So the thermometric property here, the thing we are actually measuring to figure out the temperature, is the liquid's volume. Now, for one you might not see every day, but it's super important in science, the constant volume gas thermometer. And just like the name says, it takes a totally different approach.
So instead of letting something expand, this gadget does the opposite. It keeps a bunch of gas locked into a fixed, constant volume. When you heat it up, those gas molecules start zipping around like crazy inside, and they push harder and harder against the walls of the container. That means, you guessed it, the pressure goes up. So here, our measurable property is pressure.
All right, let's get electric. Thermocouples are absolute workhorses in labs and industry, and they rely on this really fascinating electrical phenomenon to do their job.
This is so clever. You take two completely different types of metal wire, and you join them together in a loop. Now, if one of those connection points is hotter than the other one, that temperature difference itself actually creates a tiny but totally measurable voltage. How cool is that? This is called the Seebeck effect. And see, our recipe still holds true. The property we're measuring here is that voltage, which is technically known as electromotive force.
And for our final tool, let's check out one of the most accurate thermometers you can get your hands on, the platinum resistance thermometer. This one works because a metal's electrical resistance, basically how much it fights against an electric current, changes very predictably with temperature. And for a super pure platinum wire, that relationship is incredibly stable and well understood, which makes it perfect for high precision stuff. So no surprise here, the thermometric property is electrical resistance.
Okay, so we've seen how we measure temperature by looking at all these different physical properties. But this brings us all the way back to our original question. When a thermometer finally settles on a steady number, what does that number actually represent? It represents a state of balance, a state known as equilibrium. The key concept here is thermodynamic equilibrium. Just think of it as a stable, resting state where all the properties of a system have just settled down and aren't changing anymore. You know, when you put a thermometer in hot coffee, you wait a minute, right? What you're really waiting for is for the thermometer to stop changing, and that happens when it reaches the exact same thermal state as the coffee. That shared state of balance, that is equilibrium. Now, what's really interesting here is that this idea of total equilibrium is actually made of 3 parts.
For a system to be in full thermodynamic equilibrium, it needs to be in thermal balance, meaning no more heat is flowing. It has to be a mechanical balance, so no changes in pressure. And it needs to be in chemical balance, meaning no more chemical reactions are going on. A thermometer is specifically designed to measure that first pillar, thermal equilibrium.
But of course, the world isn't always just sitting still in some perfect state of balance, right? Things are constantly changing. So what do we call the journey a system takes when it moves from one stable state to another?
In thermodynamics, that journey is simply called a process. It's the path of change. But as we're about to see, not all paths are created equal.
On one side, you have this ideal, theoretical thing called a quasi-static process. This is a perfect change that happens so slowly that the system remains in balance at every single tiny step of the journey. But in the real world, things happen fast. A real process, a non-quasi-static one, occurs at a finite speed, which means the system gets all jumbled up and is temporarily thrown out of equilibrium while the change is happening.
And that leads to another crucial distinction. Those perfect, slow-motion, quasi-static processes are, in theory, reversible. You could run the film backward and return everything to its exact starting point. But real-world processes always have things like friction, which generates waste heat, and that makes them irreversible. You just can't unstir the cream from your coffee.
And finally, how a system changes depends a lot on its container. A boundary that lets heat pass right through, like a thin copper pot, is called diathermal. But one that blocks heat transfer, like the thick wall of a thermos, is called adiabatic. And this basically determines whether the system can exchange energy with the outside world while it's undergoing a process.
So, look how far we've come. We started with a simple thermometer and ended up with the grand laws governing change in the universe. And this leaves us with a fascinating and maybe a little chilling final thought. We've learned that isolated systems always move toward equilibrium, that state of maximum stability and uniformity. So if we consider the entire universe as the ultimate isolated system, what does that imply about its final destination? What happens when everything everywhere finally reaches equilibrium? Now that is something to think about.